Okay, so now that we understand the basics of rate in chemical reactions and uh, the idea of activation energy as the sort of impediment, this extra energy that we need to get from reactants to products, we can introduce this sort of final idea, which is catalysis. So a catalyst is simply just a substance that can increase the rate of a chemical reaction, but the key is that it doesn't get consumed. And so it's just there to help make it faster, but it's not actually a stoichiometric reagent of the reaction. It doesn't actually get. So to illustrate what a catalyst actually does, how does it increase the reaction, we just go back to this energy reaction diagram that we just finished talking about. And so, we've thought about this since Chem 107, right? If you have the generic reaction of A and B react to make C, the universe is going to say, yeah, I'll go ahead and drive that reaction as long as the energy, the bond energies of C are lower than what the intrinsic energies of A and B were. And that's sort of the classical idea of just a net energy lowering of a system. And that's what's illustrated. And we would just say that the overall reaction of A and B to make C has a negative change in enthalpy, or delta H. So C is lower in energy. It's a more stable state than A and B. But we know now with kinetics that energy isn't the whole story. There's also the rate at which A and B proceed to C, and they proceed through that barrier that's known as the activation energy. And that activation energy, or EA here, means that before A and B can proceed to that low energy state, they actually have to get up to this higher energy transition state geometry before they can fall back down that hill. So that's energy input to get there. And so that depends on how much kinetic energy is in A and B when they collide with each other, which is that idea of collision theory. And we said before with the Arrhenius equation, well, we just crank up the temperature and the kinetic energy of these things increases, the number of collisions then increases, and you're likely to surmount that activation energy. The other way to do that is with a catalyst. And so the purpose or the function of a catalyst is actually to not decrease this activation energy. It doesn't actually change that. That's an intrinsic property. But what it can do is it can create an alternative route between the reactants and the product. And that might be a multi-step reaction, it could be a single-step reaction, but the idea is that the high point of this curve is now lower than what it was before because of introducing this other substance. This substance could be a chunk of metal like platinum or palladium or iridium, like the ones that you find in catalytic converters. It could be another chemical, molecular chemical. It could be a variety of things. There's a huge industry built on designing catalysts that can decrease that the energy required to get a reaction to run. The idea being, if we have to add more energy in the form of temperature, that's not a very sustainable practice, right? We don't want to heat the heck out of everything to get it to run, because that comes from burning fossil fuels. So can we get these really nice catalysts that require much lower energy inputs to drive the same chemical reaction? So this is a multi-billion-dollar industry and an area of active research, especially in producing things like hydrogen gas, so that we could really develop an economy around hydrogen fuel instead of fossil fuels.